Welcome to Using Python to Detect Vulnerabilities in Binaries. I'm Terri Oda. I have a PhD in computer security, but the real reason you should value my opinion here is less about my academic credentials and more about my experience. I've been working in open source for over 20 years, and I currently work at Intel in open source security. So that means that I help many of Intel's open source projects find and fix issues before they go out the door. And also, I've evaluated a lot of external open source libraries to see how they handle security. Within Python, you're most likely to know me from my work on GNU Mailman or the fact that I coordinate student mentoring for the Python Software Foundation as part of Google Summer of Code. And both of those give me a lot of time working directly with different developer communities. So let's talk about this problem. Hopefully, if you're listening to this talk, you care a little bit about finding security vulnerabilities in software. But why binary files? And why is this an interesting problem? Let's imagine a scenario. You've been given a piece of software and told to run it. How do you know if that's a safe thing to do? If you've ever downloaded an executable off a website, you've probably done one or more of the following things. You might have run a virus scanner on the file that you downloaded. You might have verified the signatures to see whether you have exactly the right file and maybe whether it's downloaded completely. You might have checked for updates, made sure you got the latest version. And if you had some concerns about security, you might have even read the security advisories that went along with that piece of software. If you were getting something from an app store or another managed interface, you might have assumed that whoever's managing that has done some of these steps for you. Maybe that you assume that they get the latest updates or you assume they run a virus scanner. That's not always true, but we like to believe. But what if you are the responsible adult? You're the person who's managing the app store. You're the person who's shipping software. What do you do then? Before we go any further, let's just acknowledge that safe or secure is a really big and sometimes nebulous problem space. I have huge development checklists for what we think makes software more secure or more private or robust. And what exactly you should be doing as a developer is often still a matter of cutting edge research. So, as you probably guessed from the title, we're focusing on one piece, and that one piece is known vulnerabilities. That should be the easiest piece to do, right? They're known, we should be able to find out whether we have them or not. So then we have a slightly longer list. Instead of just caring about the individual packages, we're going to have to care about all the things that they depend on if we want to say that this piece of software doesn't have any known vulnerabilities. So you get a list of all the packages you use. You do the same thing we did before. You verify some signatures, you check for updates, you read those security advisories, and if you have anything that you found in your own software, you might be issuing your own security advisories. Sounds not that different. Still seems pretty tractable. Except that in practice, a lot of modern software has a lot of dependencies. So you might start with something that looks like a fairly short list, but then each of those packages has their own list, and each of those packages has their own list, and it can get out of hand. You might think I'm exaggerating, but when one of my colleagues was building test cases for a machine learning security tool, he found a JavaScript package that had 877,000 dependencies, and of course, a number of them had security issues. As a Pythonista, you might be feeling kind of smug right now because you know you've got a tool that'll help you get the list of requirements and all those subdependencies. So what you need to do is you make a shiny new virtual environment, you install what you need, and then you get it to spit out a list of requirements. If you maintain a Python package, you may have done this at some point. So let's try this with Python's cryptography. Make my shiny new virtual env, install cryptography, get some requirements, and they look pretty good. There's not that much in there. This doesn't look too scary at all. Except I happen to know that under the hood, cryptography calls to OpenSSL. And I happen to know that Python has this fancy thing where you can package binaries into your pip so that it's installed with you, do the whole batteries included thing. So what version of OpenSSL did I just install? Yeah, I don't really know. And if I didn't know it was there, I don't think I'd have any clue. So even with a language that has good tools, knowing what's in software is surprisingly hard. I'm not going to walk you through other languages, but I work in open source security and review a lot of software, and I can tell you we spot some weird cases. Uh, and if you don't believe me, ask the people who specialize in licensing because they have a lot of the same problems. If figuring out exactly what's in software is important for both licensing compliance and for security, then why don't we have tools to help us do it? And the answer is, of course, that we do. But they're fairly expensive because it takes a lot of effort to determine exactly what's in software. It takes a lot of effort to keep it up to date as software changes. And they tend to be slow because they're scanning for, well, maybe not 877,000 different types of JavaScript packages, but a lot of different common pieces of software with interesting properties. For someone who's in an organization that cares deeply about security, having a tool that's expensive and slow is a reasonable trade-off for it to be accurate and comprehensive. But sometimes you don't want the whole cake. Sometimes you just want one piece. So what if we built a tool that only cared about old versions of OpenSSL? Or maybe we could expand it to a few other open source libraries with interesting security impacts. And then we've got something that's no longer that expensive to build and doesn't have to run very slowly. So suddenly we've got something that's totally suitable for sharing with external partners or open source projects. And we've got something that's maybe fast enough to run as part of your continuous integration to give you a heads up if there's a new vulnerability you should know about. So that's what we did. It started with a little Python script that detected old versions of OpenSSL, and we've slowly built a larger tool that we now call the CVE Binary Tool. It's free, it's open source, and it comes with a bunch of different checkers to tell you about your vulnerabilities. So let's take a little look under the hood. If I've got a package and I'm a small Python script that doesn't know anything about what it's looking at, how do I guess what's there? So we decided to think like a hacker or a pen tester and go really simple. The Unix utility strings. You run it on a binary, it gives you every string that it finds that's larger than 4 characters. Some of them are kind of useless, as you can see, but some of them give you some hints as to what's in there. And if you take a look at this one, you can sort of see, maybe I have a pretty good idea of what might be inside this package. Okay, so I'm pretty sure this is going to be OpenSSL, but what version of OpenSSL do I have? Well, we can use our other favorite Linux utility, grep, which is a text search tool, to narrow it down. So I'm looking for everything that includes the string OpenSSL now. And oh look, there's a nice clear version string right there. This is OpenSSL 1.1.1d, released in September 2019. If we want to go from that to a signature, then we need to look at a few more versions of OpenSSL and start to find a pattern. So here's part of what our OpenSSL signature looks like. It's pretty obvious, OpenSSL, a number, a letter. It would be pretty brittle if you were trying to hide what was in your software for some reason, but really the purpose of this tool is to help you avoid honest mistakes in updating, and it's good enough for that. And in case you were wondering about the question of what's in Python's cryptography package earlier, it was OpenSSL 1.1.1d, and when I put together my slides, that was the latest version available, so we're good. The pattern that we see for OpenSSL is something that we see across a lot of software. You end up with a signature that looks sort of like a package name, maybe some white space, a version number, maybe some more white space, and maybe some extra information. It doesn't work for all software. One of my favorite unusual ones is SQLite, where it doesn't have a version string that we can parse directly, but it has this big source ID string. And that's sufficiently unique that we can then take it and verify it against their published information. So when you detect SQLite, you look for this big hash, and then you map that hash back to the version. But it's definitely true that there are libraries that we can't detect easily, and for now, we've just been making a note of them and moving on. Once you've got a version number, how do you go from that to a list of known vulnerabilities? So we could do fancy web scraping for everyone's website and read all of their security advisories, but that's a lot of manual work and we don't have to because there's this glorious pile of JSON that contains all known enumerated public software vulnerabilities. It's called the National Vulnerability Database, which is a bit of a misnomer. It's actually pretty international. But the important things is that it's public domain and it's pretty easy to get. If you take a look inside the JSON, you can see a bunch of information about each vulnerability. They call each one a CVE, or Common Vulnerability and Exposure, and it's got a unique number assigned to it. And the system allows for ranges, so you can see here in this CPython issue that this description text tells you about 3 different ranges of versions that are vulnerable, and then down below it's got an appropriate way to see them in machine-readable code. Once you've got the range information for finding vulnerability, then you can use package resources parse version function to figure out whether the software you found falls within that range. And that works pretty well, but we had an interesting issue here because parse version assumes that any letter following the numbers is something like a release candidate or a alpha or beta, and that's not how letters work in OpenSSL version numbering, so we actually had to convert that last letter into a number to make parse version behave the way we expected it to. The other thing to note here is that while there are these beautiful machine parsable data ranges, our experience has definitely been the data isn't perfect. The most common problem that we've seen is sort of off by one type errors where the description says that all versions before 8.4 are vulnerable, and then the data says version 8.4 is vulnerable and no others. It's not really hard to report these things, but you do have to remember this is a large database that is filled in by humans, and sometimes humans make mistakes. Now that you have an idea of what's going on under the hood to make the detector work, let's talk about how to actually use the CVE binary tool. We've got a nice pip package, so you should be able to just pip install CVE bin tool and then run it on any directory or file you want. You will need Python 3.6. Once you do that, it'll scan through whatever file or directory you've given it, and if it finds something it understands, so something that it has a checker for, it'll try to find the version. If it finds a version with any known vulnerabilities, it'll give you a list of them. Thanks to our students, we're in the middle of improving the output for the tool, so it may look different soon, but this is the current console output. But my experience working as a security engineer is that often when people get a list of CVEs, they're going to want to triage them. Maybe track what versions you need to upgrade to fix them, put notes if there's any mitigations, figure out where it came from. We don't have a triage tool built into the CVE binary tool, but we do provide a comma delimited format, which is suitable for people to import into spreadsheets so they can work with the data there. And finally, we have a JSON output format, which is intended to be the machine parsable one. Uh, we're planning to use it with the machine learning tool diffml to help us learn about what packages should and shouldn't be installed from various known software repositories. But we're hoping that people will find other interesting ways to use it if they want to integrate vulnerability data into their processes. Sometimes it's not obvious to people, but the bin part of CVE bin tool refers to binaries. We're really only scanning binary files. And if you recall how simple the signatures are, you can sort of see why we might have done that. If you're scanning through all of the text help and documentation, it'd be pretty easy to get a false positive off of something that says you need at least this version of this package. The other thing is that if you have source code, you probably have other tools available to help you figure out what's in your build, or you might already know, so that you probably shouldn't just be using heuristic signature detection to figure that out. You might as well just use the data directly. But since we have this parsed database of vulnerabilities already, we might as well build a tool to help you with that. When you install the CVE binary tool, you also get a utility called CSV to CVE, which you can use against a list of known components. The CSV part refers to the comma delimited format that they're expected in. So that lets you skip the more heuristic binary matching, potential for error. You don't have to worry about whether a checker's been written for something you care about. It just gives you a list of known vulnerabilities out of the same database. So you could take something from something like your requirements list or your build scripts and just get a list of anything that needs a version bump for security reasons. And if you haven't been responsible for the security of software recently, you may not know, but it's surprisingly easy to miss this without automation, especially if you're talking about something that's a couple of dependencies levels down. So this is what the output for that used to look like, but I literally just merged a patch this morning that makes it look exactly like the output from the main tool. So that'll be a little easier to work with. The big limitation on this utility right now is that you need to get the list of NVD vendor product pairs in your CSV file for it to work. These aren't really hard to find with a quick search of the database, but they're kind of hard to automate because of name duplications, different packaging decisions, and sometimes a given package doesn't have a vendor product pair yet because it hasn't ever had a CVE. So if you were hoping to just take your requirements.txt that pip generated for you and get a list, it's not going to work without a little bit extra help. Uh, we've got some students who put forth some good ideas on how to improve this, but basically this is one of those cases where we're giving you a slice of cake, not quite the whole thing. So you've run the tool and it found something. Uh-oh, now what? Number one, learn. Go and look up whatever it is that it seems to have detected. You can usually just put that CVE number into a search engine of your choice, and it'll come up with links to find out what the problem is, information about how to mitigate it, and when it was fixed. As I said earlier, the data isn't perfect, so sometimes you'll find out that it was detected in error. You can report those to us or to NVD, and we can get them fixed. And every once in a while, you'll be using something that has a backported patch, so the version number doesn't line up with when the fix happened, and then you don't have to worry too much about that one. But most of the time, you're going to go on to step 2, update. So it's usually less work in the long run to just update to the latest available or a long-term support version if one exists. If you're the responsible adult in the room, don't forget to release a new version of your packages with updated dependencies if you need to. That'll help a lot of people. It's often tempting to backport patches. I'm not a huge fan of that because it can introduce new bugs pretty easily. But if you do that, be aware that the CVE Binary Tool is not smart enough to detect it, so you will continue to detect that one even after you've fixed it. And finally, if upgrade isn't possible immediately or there isn't a fix yet, you might want to look at step 3, mitigate. So look for things you can do to reduce your risk. These are usually things like disabling the affected code or changing configurations to be more secure. If there are known mitigations, they're usually included with the CVE data that you found in the learn step. So you should be able to just go ahead and do those things. And if you're the responsible adult who's releasing a package, don't forget to tell your users what best practices should be for your code if you know them. I've covered what we think are the most common usages for the CVE binary tool, but there are a number of other options available, like extracting compressed files. You can always get a list from the manual or running the tool with the help option. And as I said, we've got a lot of new development going on right now, so there should be new stuff happening pretty regularly. So that's the CVE binary tool. Now you know what it is, how it works. You might be wondering, how do I use this knowledge to help make the world more secure? Number one, please use the tool. We made it for the world. We want the world to use it. If you do one thing after you're done watching this talk, go pip install it or grab the latest from GitHub and try running it on something. My favorite thing to do is to run it on /bin or user lib and just see what it finds. It's kind of fascinating because in any reasonably large operating system, there are always some things that have known vulnerabilities in them at any time. So it's pretty neat to be able to see what they are. And remember how I said back at the beginning that we couldn't really justify recommending big, expensive packages to tiny open source projects? Well, this is it. We built you a free open source package to help make this easier. Please use it. Stick it in your continuous integration. Tell us if it works for you. Tell us if it doesn't work for you. I really want to know. Second, if you try it out and you think it might be useful, you can contribute to it. There's a particular checker that you'd like to have that's not there yet. This is an open source project. There's 4 steps to adding a checker. You need to choose the software that you care about. Then you need to find the vendor product pair that matches the product in NVD. Be aware that sometimes there's more than one vendor product pair, often because the product name or owner has changed over time. Don't worry, we've got code to handle that. From there, you need to look at the strings and find a version signature. We showed you how to do that with OpenSSL. It's going to be pretty similar in a lot of cases. And finally, you develop some tests against real binaries to show that this checker works in the real world. And if you don't have time to do all of these steps, doing any number of them is still really useful, especially just choosing filing an issue saying this is a checker that I think would be interesting is really helpful. We have a regular stream of new contributors who are always looking for new bugs to work on. And one of the reasons that we have regular new contributors is that we've been participating in a number of events designed to bring new people to open source projects. The one that's going on right now is Google Summer of Code, which is a neat event where we provide mentorship and Google pays students to work on open source projects. As I mentioned at the beginning, I coordinate this mentoring effort for all of the Python Software Foundation, but I also mentor students directly as part of my day job at Intel with the CVE Binary Tool project. So the students come in, they learn a little bit about the project, they fix some bugs, and then they propose ideas for 3-month-long things that they'd like to work on. This is our second year doing it, and what I've learned is that a lot of the students could use help understanding how people would actually use this tool, what features might be useful, and what checkers people want most, and the like. So that brings us to number 3, mentor. If you're pretty good at code review or love hunting down weird bugs or know how to help people fix their Git trees or just like talking about what it's like to have a job in software development and open source, it's a pretty fun thing to do. Because of the pandemic this year, Python has way more student applicants who are eager to find a job that doesn't involve being on site anywhere, and way fewer mentors because a lot of our mentors are very busy with pandemic related things and not having childcare and the like. So if you're one of those people who feels like they have a little extra time in the pandemic, your help would be especially appreciated this year. And if you're not a person with extra time, I hope you can at least feel good about the fact that Python is doing what we can to provide remote jobs and mentorship to students this year. And that's it. Here's that URL for the CVE binary tool again. It may be a small piece of the whole vulnerability detection cake, but I hope it's enough to be useful and filling. Please go forth and try it out and let us know how we can make it better. Thanks for listening.